Hello viewers. Hello viewers. Welcome to Adam. Today we are going to solve a simple problem based on SFT and GMB. So here you can see there is a fixed support at A and there is a UDL throughout the beam. The beam is of 2 meter and there is also a point load at a B. So let us try to solve this. So as you know, firstly we need to make the FBD to find the supports. Then we need to find the shear forces and bending moments to make the diagram SFT and VMD. So these are the steps. So let us try to follow the steps and come up to the answer. So firstly, we need to make the FBD. As you can see, we can make the FBD by converting the UDL. So this is the UDL into a point load and now give the reactions at A. So there are 3 reactions at A. So because there is a fixed support at A, there will be a Y direction force, there will be a X direction force, let us call it FAX and FAY. And there will be also an moment. So let us call this at MA. We need to convert the UDL into a point load, which will be 2 kilonewton into 2, which is 4 kilonewton. And there is a point load at V. So this is V, this is A. So this will be at the 1 meter from A because the center of the entire UDL will be at midpoint of the loading, which is at 1 meter from A. So let us try to understand what we did here. So firstly, you could have observed that there are 3 unknown forces here, MA, FAY and FAX. So whenever you have a hinge support, as you could recall from the earlier discussions, that there will be an FY and FX force if there is a hinge support. And if there is a roller support, then there will be a vertical force only, which is FY. So there is only one unknown force here. There are 2 unknown forces here. But whenever there is a fixed support, there will be 3 unknown forces. So this is a fixed support. So there will be a horizontal vertical force as well as a moment, which is an unknown moment. So these are the support reactions which are there according to the different types of supports. So as you can see in the first condition, there is Fy and Fx are the unknowns. There is Fy as unknown in the second, and there is Fy, Fx, and there is also a moment unknown in the third. So these are the conditions. So in our case, there is the condition is of the third type. So there is also an unknown moment of Ma, Fy and Fs are the unknown forces. So we know that we could find all of these using the equilibrium conditions, which is summation of Fx is 0, summation of Fy is 0, and summation of moment at any point is 0. So let us apply the first condition. So the first condition is summation of Fx is 0, summation of Fx, we only have Fax as the force, and there is no horizontal force throughout the beam except Fax. So Fx will go to 0. This is the first equation. And we have Fy as a 0, summation of Fy is 0 as our second condition. So Fay, let us say, is the first Fay force, and the second is minus 4 kilonewton, and the third is minus 3. The minus 4 is due to the UDL, and minus 3 is due to the point force at B. So it goes to 0. So Fay comes out to be 7 kilonewton. From this let us call this equation as equation number 2. And we also have an unknown moment at A. So what we can do is just apply this condition of summation of moment at A is 0 because of equilibrium condition, and that will give you the unknown moment. So let us say some unknown moment we have at MA, let us say MA. And we also have 2 clockwise movements. So there is this, let us consider clockwise as positive. So this clockwise, it is considered as positive and anti-clockwise as negative. So there are 2 clockwise movements. So 4 into 1 is one of them for the UDL. So let us say plus 4 into 1 plus also 3 into 2. So the movement is force into perpendicular distance, which is 2 here, and the force is 3 kilonewton. So that is why the movement is 3 into 2, and because of the UDL, movement is 4 into 1. So it comes out to be 3 into 2 is 6 plus 4 is 10. So it will be minus 10. You could have always guessed it because there are 2 in the clockwise direction for moments. So the reaction at A must be anti-clockwise to balance them out, or else the beam will be unbalanced and beam will be not be straight, but a bended beam, like something like this, because there are two clockwise movements. So to balance them out, there should be an anti-clockwise movement at A, which comes out to be -10. So that is how you can do the question. So next thing is, as we have found out the support reactions, so we need to find the shear forces at every point. So let us now calculate. So as you can see in the left diagram, so if we calculate shear force just right here, which is just right of A, the shear force, let us say shear force just right of A. So just right of A, we are considering forces on the left, which is FAY in the vertical direction only. So it will be FAY, which is 7. So it will be 7 in the positive direction. So the sign convention for this is, whenever you are calculating on the left side of the beam, so if you are making cross section, let us say somewhere here, right of the A, and you could consider like all the right hand side forces, or on the left hand side forces. So what we do generally is we consider left hand forces. So left hand forces are positive in the upward direction and negative in the downward direction. And if you are considering right side forces, it is just the opposite of this. So downward is positive, upward is negative. So to avoid the confusion in this sign convention, we always try to consider on the left side forces for shear forces. So just to avoid the confusion in the sign convention. So as you can see, we just calculated right of A and considering the forces on the left, which is just the reaction force at A in the upward direction, which is FAY, which is acting on like this, FAY, which is equal to 7, as we have calculated earlier. So we also can calculate shear force just before B. Just before B, we have 7 minus 4 because of this UDL, which you can see from the FBD which we have. So here is our FBD. So if you just make a cross section here and consider all the left side forces, there is a 7 in the upward, which is FAY, and 4 in the downward. So it will be 7 minus 4, which is equal to 3. So 3 will be just before B. Just before B there is 3, and add B. So shear force at B will be 3, and there is 3 in the upward and 3 in the downward. So it will be 3 minus 3, which is goes to 0. So these are the shear forces at every point. So using this, we can make our shear force diagram, such as shear force at A is 7. Shear force just before B is 3. So this is 3. And at B, let us say this is A, this is B. At B, it is 0. So you can just join like this because there is UDL. So the variation will be linear. So this is your shear force diagram. So whenever you have a load case, such as which is UDL, the shear force diagram will be inclined line, or let us say this is inclined line. And the bending moment variation will be a parabola there. You can just remember this using this condition, that the load is 1 degree below the shear force, which is 1 degree below the bending moment. So if the load is constant, then the shear force will be linear and the bending moment will be parabolic. Let us say it is some types of like constant load, like UDL we have 2 kilonewton per meter here, which is a constant loading throughout the beam. So the shear force becomes linear here, and the bending moment will become parabolic here. And if we had load 0, because let us say there is no UDL in between and there is no load, so load condition is 0. So 1 degree above will be just the constant shear force, and 1 degree will be linear bending moment. So that is the conditions which we have, that if the load is constant, then the shear force is linear and the bending moment is parabolic. 1 degree above is what you can remember. You can remember this relationship. It will become easy for you to understand what will be the variation of shear force and bending moment according to the given load. So this because of a UDL, we have given a linear line here in the shear force diagram. And let us consider now the bending moment at every point. So bending moment at just right of A, and just right of A. Again, there is a sign convention which you need to follow. The sign convention is, whenever you are calculating from the forces which is on the left of the beam, then the clockwise is positive, anti-clockwise is negative, and on the right of the beam, the clockwise is negative and anti-clockwise is positive. So just remember this sign convention. Where you can just remember the upward one, then that on the left of the beam, if let us say A, B, C, and I have cross section just before B, and I have to calculate, which I can do either by considering forces on the right or considering forces on the left. So this is on the right side, that BC, and the A will be on the left side. So if I am calculating using the A load or and the A side load, which is on the left of the cross section. So this is my cross section. This is on the left of my cross section. So it will be clockwise will be positive and anti-clockwise will be negative. So that is just the basic sign convention here. I'll just have this. Yeah. So now let us look at the bending moment before B. So bending moment before B. So bending moment when you are, let us say you have crossed the beam at here. As you can see at the right, there is like no force, because just left of B, it will become 0. So it should be 0 on the left also. We can just cross check this. So at the upward force, there is a 7 kilonewton upward force at A. There is a downward force of 4 because of the UDL, and there is anti-clockwise moment of 10. So the moment will become 7 into perpendicular distance, which is 2 in the clockwise direction. So it is positive because we are considering forces on the left now. So 7 into 2 minus 10 because of anti-clockwise moment, and because of the UDL there will be 4 into 1, which will come out to be 0. So bending moment before B is 0. That's how you can calculate bending moment at A and B. And now you can just make the bending moment diagram, which will come out to be like this, that bending moment at A is minus 10, just right of A is minus 10, and V it is 0. So as you can see, it is varying parabolically and not linearly, because the shear force diagram is more linearly. You can just remember the earlier thing that load, shear force and bending moment are always 1 degree above the previous one. So the shear force, if the shear force is linear, then the bending moment diagram will be parabolic. You can also derive this by the following condition, that the shear force will be dm by dx, and the shear force by dm will be load. So this is the basic condition between load, shear force and bending moment. So whenever you have, let us say you have a shear force which is linearly varying, let us say some mx plus c, so you can just follow this condition, which is, so this is not equal, sorry. So this should be that shear force is equal to dm by dx, yeah. So you can just take this in the other side. So let us say shear force is mx plus c, then you can just take into other side and integrate, which will become your bending moment. So bending moment comes out to be some mx square plus something like cx plus dv, which will be parabolic in the nature. So if the shear force is varying linearly, which will be the case in the UDL, so the bending moment will vary parabolically. If it's the case that your load is uniformly varying load, not uniformly distributed, which is let us say triangular load, then your shear force diagram will be parabolic, and your bending moment diagram will be third degree curve. Let us say some x cube variation will be there in your bending moment diagram. So that is just the basic concept, that the shear force, load and bending moment is related like this, that the shear force is 1 degree lesser than the bending moment and the load is 1 degree lesser than the shear force. You can just remember that whenever the shear force variation is linear, the